Hello, BC students. Here we go. I hope you're having a good day. You should have out your notes for review 8. Now, third and fourth ended in slightly different places, so I'm going to pick up where third left off and fourth just hang for a second, and we'll be right back to where you were. It's only a minute or two difference, okay? So the idea yesterday was trying to estimate area in the curve using rectangles. The gradual thought is the more rectangles we do, the less error there is. So we're going to work towards trying to get the error down to nothing. Imagine if I drew y equals x squared plus 1, but really wide, so it was a little more helpful picture, and I ended it at 8. Now we talked about we're going to divide this into mini rectangles, and it starts by making the bases. The bases are small changes horizontally, and they come from the region width divided into n chunks. Now, if we did 2 chunks, then each base would be 4. If we did 4 chunks, then each base would be 2, and so on. But we're going to just let it vary in chunks. Now, here's the part where a visual helps. If each base is an 8 over n, then this first mark at which I draw a height for my right-hand rectangles would be an 8 over n, and the rectangle would look like that. The height would be f, height 1 is f at 8 over n. If I then went another 8 over n over, now the temptation is to say 16 over n, and that's true, but instead, looking for patterns, think of it as 2 times 8 over n. And if I drew the height there, height 2 is f at 2 8 over n's. Now we can keep doing that. Height 3 would be f at 3 8 over n's. Height n would be f at n 8 over n's, or 8. That's my last rectangle, all right? Now, along the way then, we're going to be counting up how many over 8 over n. So if I did this, the area would be the base, which I could factor out because they all have an equal base, of 8 over n. That's the base of every rectangle. The first height is f at 1, 8 over n. The next height is f at 2, 8 over n's. F at 3, 8 over n's. Generally ending at the nth 8 over n, or f at 8. Okay, now we could crank that out, but that's expanded notation. And the name makes sense, I think you'll agree. Better would be less writing, and that's summation notation. Now remember, summation notation handles adding a pattern. I think you'll agree there is a pattern at work here, and there is addition. To use summation notation, you have to locate where the counter is, the thing that's counting up by 1. And it's the mark of how many 8 over n's you've gone up. That's going to be the counter variable. I'll let that equal I. Now in summation notation, you are going to throw in everything you see there. First of all, I'll have an 8 over n. Now that could be out front of the sum, or you could put it in. Either way, it doesn't matter. But then inside, I want to always multiply by f at, and inside the f is always the same, the parentheses are always the same, the 8 over n is always the same. What is changing and counting up is the how many, 8 over n's. Now remember, here is the first I value in. And the first I value in, it started at counting at 1. This is the last I in, the last I, and in this case, it's n. Now, that's pretty simple heavy. What does it all mean? Well, we could use that to get an estimate of area under the curve using any number of rectangles I want. Now, let's check this. Say I wanted to use 4 rectangles. I could put into my calculator I equal 1 to 4 of 8 over 4, f of I times 8 over 4 or 2, right? Now, if I plug that in my calculator, it would look something like this. I'd start by, get out your calculators, get out your calculators. I forget when I'm not teaching with you in front of me, I forget to give you time here. In your calculators, go to the graphing menu and put in the function x squared plus 1. Okay, now go to the home screen, and we're going to do summation notation. Now, the summation notation is in the catalog of functions right next to the 9. Look right next to the 9, hit that button, and in the middle row, you'll see summation notation. That's sigma. Choose it. Now, I'm just going to type in exactly as I had it. I equal 1 to 4. In here, I have 2, not sure why I use those parentheses, times the function. Remember, the function can be found in vars if you define the function. And inside is 8 over 4 or 2i. Hit enter, and you get 248. Now, had I had a little more time, took a little more time, that's what we would have had in our first example right here if I had calculated out that 4 rectangle RRAM on x squared plus 1. 248 is what we would have had. Now, say I wanted a little more precision. I could do more. I could do ugly stuff like n equal 57. Well, 572. Say you wanted to break it up into 572 rectangles. Yep. You could just go 572 for the upper bound. Now the delta x is 8 over 572. F at I times 508 over 572, rather. Calculate that, and I assume it would be much closer to the original or the true value, right? Now, that said, would you try and write an equation for this using, to estimate the area under the curve of this bad boy using n right rectangles? Summation notation is up to you. Actually, sorry, expanded notation is up to you. I definitely want to see summation notation. Then use your rule with, well, let's say 100 rectangles. Let's see what your estimate is. Ms. Smith, if you pause the video while they tackle that, and then when it looks like they're about ready to go, hit play. Okay, now here we go. You might write this down. To bypass expanded notation, the idea is we're adding a bunch of rectangles. The base is delta x, and the height is f at different x values. And delta x comes from the region width divided by n chunks. X sub I comes from the starting value, the A, plus delta x I times Now, that'll help and make more sense as you go, and maybe that's where you ended, but it's nice to have in your notes this bad boy right here. So if I follow that as a blueprint, delta x is 2 minus 0 over n. X sub I is starting from 0, I'm going over 2 over n chunks I times. Remember, that's the idea of starting at 0. The first x is 2 over n. The second x is 2 over n twice, and so on. Yeah? The 0, I'll talk about in a minute. You might be thinking, why is that 0 there? Why even include it? I'll explain in the next 2 slides over. So if I wrote this here, it would be starting from I equal 1 to n. That's always the case if there are right rectangles. It goes from 1 to n. Delta x is 2 over n. And the f at which you draw your heights is 0 plus 2 over n I times. F at 2 over n, f at 4 over n, f at 6 over n, drawing a rectangle up at each of those marks. Now, if I said n equals 100 to check my work, I would be plugging in 100 for each n. And I get 2 over 100, yes, 150th, f of 150th I. And I could get a really good estimate. So let's start and do that. I'm going to scratch out or erase doc B and start from scratch. I start by plugging in the function. It's the square root of x plus 1. I hit enter. Graph looks great. I go back to the home screen. I start with my summation. It's in the button next to 9. The summation is in the middle row. Type it in as you wrote it. I equal 1 to 100. I'm going to this time put the 50 over n out front. You don't have to. Nope, 50 over 100. What am I doing? Sorry. That's 1 over 50 out front. Sorry about that. That 1 over 50 can go inside or outside. It's kind of like a constant in an integral. It's the same either way. It's going to be distributed either to every term or factored out front. Inside is the function at 1/50th I, or I over 50 if you like. If I did this well, I get an estimate of the area as 2.80475. That's my estimate. I hope that's what you got. How'd you do? Okay, hopefully that is catching. Now, let's go from there and work backwards here. This time, instead of giving you the curve and the region, I'm asking you to give the curve and the region from the summation notation. We'll try the first one together. Remember, this here tells you the region width. Delta x is 3 over n. That means the region must be 3 units wide. So let's go with the assumption that the interval is 0 to 3. Okay, now go into the inside and that'll tell you what the function is. It looks like the function f of x is 2 minus 3 over n I all cubed phew. Now it seems like this is the x sub I because it's 0 plus 3 over n I times. So all the other stuff is the function. So the function, which I'll call f, is 2 minus x cubed. Okay, now hopefully that's tracking, but I don't have a field, so you try. Okay, if you need more time, pause the video, and here goes. I start here. This tells me the region width is 5 wide, assuming I started at 0, which is a large assumption, but let's go with it for now until we get filled up to the harder. If this is the x sub I, 0 plus 5 over ni, I see 2 of them though. That means there's 2 x's. So if this is an x and this is an x, then the function must be 2x cubed plus x. So far, so good, people? Okay, let's try a little harder. I told you it's an assumption that the region starts at 0. Let's try one where the region doesn't start at 0 and see how that changes things. I hope you're doing okay. If I were to real quick sketch this, I'm going from 1 to 8. And I'm going to bust this into right rectangles. Let's first find delta x. Delta x is a total region of 7 wide divided into n chunks. Now, in your picture, in your notes, mark this. When I go over 1 delta x, starting from 1, that would take me to my first x of starting at 1 and going over a 7 over n and drawing the height. Now when I go one more over to get to x2 is starting at 1 going over 2 7 over n's, and I draw the height. So generally speaking, x sub I is starting at 1 going over 7 over I times. So in my summation notation, my area is delta x, 7 over n, and now the x sub I, I'm going to keep writing universal here just to get it in your head. Delta x for the base times x at different points for the heights. The delta x is 7 over n. The x at which you draw, x sub I, depends on where you started, 1, plus how many delta x's you've gone over as counted by I. So in this case, it's 1 plus 7 over n I times. I, if it's Rm, still starts at 1 and ends at n. You try one, you try. All right, if you're confused, you might write these steps down for reference. You always find delta x first. In this case, it's the region width, which comes from 5 minus 1, divided into any number of chunks. So delta x is 4 over n, the base of each rectangle. I think I like it if you give me the general. The universal is just delta x, which will eventually become dx, f of x sub I, And the Greek S, sigma, will eventually become a Roman S, which we call an integral. But that's the fundamental theorem to come. If I plug in delta x, in this case, is 4 over n. X sub I is where it starts, which is 1, plus 4 over n I times starting at 1 and going to n. And if I wanted to, I could use my calculator to get any number of rectangles and get a better and better and better estimate. You can do 1,000,000 rectangles. All right, now let's go again backwards. Try from these set up integral or summations to tell me what the function is and what the region is. Oh, sorry, we're doing this one together. My bad. So here's delta x. Cool. But is that 0 to 3 or 1 to 4? It's 3 wide, I know that, but where does it start? Now, let's assume that this guy is the start. If it starts at 2 and goes 3 wide, then it would end at 5. Now, if this whole thing is the x sub I, then the function must be just x cubed. Now, if you're like most curious classes, you might say, well, wait a second, how do you know that 2 is the starting value? How do you know that's not part of the function? In which case, if you say that's part of the function, you might say the region goes from 0 to 3, and the function is 2 plus x cubed. That's a fair point. To which I say both are correct. If you think about this graphically, I'm going to graph this really wide. Obviously, x cubed grows really quick, but we're going to graph it really wide. This from 2 to 5 might look this way. That's really terrible. Okay. Now, if I then graphed this graph, 2 plus x cubed, then it's shifted up to, it looks like this. 0 to 3 is that same thing that's 2 units away from the inflection point. I screwed up my scale so bad that they look different. But the point is they're the same amount of graph and therefore the same area. It doesn't matter if you think of that starting value as 0 or 2, you'll get the same. In fact, there's infinitely many. Maybe the function is 1 plus x cubed, and then you would have to adjust a little. That's fun. Problems will come to that, right? So would you give me 2 possible solutions to the log 1 below, please? 2. Okay, you might have said it's log of x from 4 to 9. you said the 4 is the starting value and 5 is the width, so 4 to 9. In which case that whole inside x sub I is the start plus the delta xi times, fair enough. All right. If, however, you said this only is the x sub I and the starting is 0, then you'd say it starts at 0, goes 5 wide, in which case the 4 is part of the function, and f of x is log of 4 plus x. Through shifting, you would see they are the same. Okay, now let's go. Now we're going to do some infinite rectangles. The whole goal is not to do 100 rectangles or 572 rectangles, but infinite rectangles. And so that's where we're headed next. The first thing you're going to do is set up your summation notation like we were just doing. Would you give me the function for area based on any number of rectangles, the summation notation? Sketch that out. I'll give you 20 seconds. Okay, so our delta x is 4 over n. The function is 0 plus 4 over ni times. If you didn't write the 0, I'm fine with it. If I do right-hand rectangles, it'll go from 1 to n. Now, in terms of getting towards fleshing this out, we're now going to use the function given. If you want to move the 4 over n outside, that's okay. The function is x cubed plus 2x, which is blank cubed plus 2 blank. And in each of those places goes 4 over ni times. All right. Now then, here's where it's easy to get stuck. Okay, great. Now what? Now this algebra you won't show. But for your note purposes, let's be clear. This would be 4 over n out front. And when I equals 1 goes in, you'd have a 4 over n times 1 plus a 2 times 4 over n times 1. And that would be your first result. Then when I equals 2 goes in, you get a 4 over n, this should be a brace, I guess, a 4 over n twice cubed plus a 2, 4 over n twice. And then just for one more, when I equals 3 goes in, you'd have a 4 over n 3 times cubed plus a 2, 4 over n 3 times, and so on. All right. Now imagine the algebra. That's still, I mean, what the heck? That's huge. I don't even know what to do here. Now, what we're going to do is collect like terms. Look at all of these bad boys. Oops, this was supposed to be cubed. Look at all of these bad boys here. Now, this is addition, and addition is commutative. So I could easily put all of those together and rearrange them and say I could have 4 over n once cubed plus 4 over n twice cubed plus 4 over n 3 times all cubed, and so on. I could get all those together. And then I could regroup and put all of the 2 bad boys together. And they would be 2 4 over n once plus 2 4 over n twice. And I could group those all together. Still is a mess. Still don't even know what to do, but we're getting somewhere. Now for this here, each of these has a greatest common factor. I could take out a 4 over n cubed, and inside would be left the 1 cubed plus 2 cubed plus 3 cubed plus, and so on. Likewise in this bad boy, they all have a common factor of the 2 and the 4 over n, so I could take out a 2 and a 4 over n, and inside is a 1 plus 2 plus 3, and so on. Stick with me. Again, you're going to be dropping all this out, so don't sweat it. Now then, if I wanted to write this a little cleaner, I could say it's 4 over n times, and in this summation notation here, I would have a, let me go with a brace there, 4 over n. This could be a 4 over n all cubed, and this is nothing but the sum of cubes. I being the counter going from 1 to n. This whole thing is also a summation with an 8 over n out front of accounting 1 plus 2 plus 3. That's an easy pattern. It's just I starting at 1 and going to n. Now that is what you'll typically jump to from there all the way to there. In other words, you're going to isolate the I in the summation and pull out everything else by a Grez-Conf factor. So that you'll actually skip over quite a bit of the algebra. I just wanted you to know that you could do it and why you could do it. That was fun. Now then, great. So what does this equal? 1 cubed plus 2 cubed plus 3 cubed? Well, it will kind of depend on what you went through. It could be lots of different things, but there is a formula. Look at the top of the page. There's formulas for sum of cubes and sum of i's. The sum of cubes, if I use formulas, the sum of cubes, if I use in place of this there, baby, is n times n plus 1 over 2 all squared. And the sum of i's is n times n plus 1 over 2. Phew. Now, eventually you won't even clean that up before you take the infinite limit. But I am going to clean it up because it's pretty gross. So if I distribute this, I'm going to call that 256 over n to the 4th, n times n plus 1 all over 2 all squared, plus, distribute that, I get 32 over n squared times n plus 1 all over 2. Now I could obviously further simplify that out, but I hope you'll see that you don't need to. What did you find after all that work? A formula that will give you the area based on any number of rectangles. If I wanted to do one rectangle, I could plug in n equals 1 and I'd get a one rectangle estimate. If I wanted to do two rectangles, I could plug in 2. But the end goal is to take the number of rectangles to infinity. Now, I don't want to rewrite all that. That's why I attached a name to it, A of n, area as a function of how many number of rectangles you use. Now, we're doing end behavior. Now, look at the powers here. If I take the limit as n goes to infinity of a sub n for this first, how do the powers work out? The denominator is n to the fourth. The numerator is n to the fourth. And so the limit is the ratio of the coefficients, 256 on top. Be careful. It's not 2 in the denominator, it's 4. The limit of this, look at the powers. N squared in the denominator, n squared in the numerator. The limit is the ratio of the coefficients, which is 16. The area, therefore, is 64 plus 16, or 80, the perfect area. Now, that is pretty doggone gross. The algebra sometimes gets a little hairy, but that should get you started. That'll do it. I hope you're as tired as I am. You should be good on review 8. Your homework is to turn in review 7. Turn in review 7 today in class. I'll check the answers. We did most of them in class. Your homework is to finish review 8, and review 9 is a layup. It's a softie, but yeah, 8 and 9 due Tuesday. Sorry, but I'm glad I'm not here to hear the booze. Goodbye.